Huge astronomy news this week as Philae, the little lander that could, finally woke up and started communicating with Earth again. If you'll recall, back in November of last year, the Rosetta mission successfully landed a lander on a comet for the first time ever. Or I should say somewhat successfully, as a few things went wrong. That's to be expected, of course, in a mission that started 10 years ago. And also in space, no one can hear you scream, "My thrusters aren't working." And so that's exactly what happened when the lander got to the comet. The thrusters weren't working and the harpoons that were supposed to anchor it to the comet failed to deploy, which all told made for a very rough landing on the comet, causing Philae to bounce a couple of times and land in a less than desirable position. Philae was supposed to be powered by solar panels, but the position that it ended up in made it so that it couldn't collect enough solar energy to provide power to the lander. And so the engineers running the operation only had about 60 hours of battery life in Philae's primary battery, during which they frantically gathered as much data as they could and tried to reposition the solar panels in such a way that they hoped maybe, against all odds, eventually, as the comet got closer to the sun, the panels might be able to start to pick up some solar rays. That would also be aided by the fact that the comet would disintegrate, lose mass, as it gets closer to the sun. And amazingly, that's exactly what happened. The funny thing is that solar panels aren't necessarily considered the ideal way to power a mission like this. Much more commonly used is the nuclear option, RTG, or radioisotope thermoelectric generators. RTGs use the heat generated from a decaying plutonium isotope in order to provide just enough power to keep a lander like Philae going. And for a very long time, NASA has been using RTGs for just that purpose. But Philae and the Rosetta mission were launched by ESA, the European Space Agency, and they unfortunately don't have access to the technology to make RTGs. There are several reasons why ESA doesn't have access to RTGs, like, for instance, the fact that the plutonium used is man-made and it costs a lot of money to produce it. But also, there are political reasons. There's the perceived danger of placing radioactive material on top of what is essentially a giant bomb. And also, there are treaties in place that make it difficult to trade nuclear material and shoot it into space. RTGs have been in a number of failed missions, and they have been responsible for spreading plutonium around places like Russia and Madagascar. But since then, the safety design has gotten a lot better. Even by 1970, the Apollo 13 RTG made it to the bottom of the Pacific Ocean completely intact and with no environmental contamination, at least for the next 800 years or so. But by that time, I'm pretty sure the human race will have evolved gills or some sort of immunity to radioactive material, right? NASA and many other scientists and engineers believe that the risk is low enough to continue using RTGs in their missions. Although in 2011, NASA launched the Juno mission, which is the first mission to Jupiter which will use solar arrays instead of an RTG. And the reason for this, NASA explained, was the increased cost of plutonium and also the increased quality of solar arrays in very low light situations. So RTGs aren't necessarily always the best for every mission, but it's a shame that ESA isn't allowed to make that call. Their hands are tied by political red tape. And because of that, there are these times when they're going to have to use suboptimal technology to reach their incredible goals. So while Philae was saved by the ingenuity of their engineers and also by the serendipity of comet degradation, it's a shame that they lost about 7 months of scientific data that they're never going to get back.